The overall goal of the following procedure is to determine the minimum inhibitory concentration for dalbavancin using the broth microdilution method with a focus on the key steps that are unique to dalbavancin. To do this, stock and intermediate dilutions of dalbavancin are made in DMSO, and final dilutions are made in cation-adjusted Mueller-Hinton broth supplemented with polysorbate. The dilutions are dispensed into a 96-well plate and inoculated with a standardized suspension of bacteria. The plate is then incubated for 16 to 24 hours and examined to determine the minimum amount of dalbavancin required to inhibit bacterial growth. Adherence to this standardized method will assure consistent results with both clinical isolates and, as shown here, quality control isolates.
Dalbavancin is a semisynthetic lipoglycopeptide antimicrobial agent that was approved in May 2014 by the FDA for the treatment of acute bacterial skin and skin structure infections caused by gram-positive organisms. This method describes the standardized broth microdilution susceptibility method for dalbavancin, which includes the use of DMSO for preparing stock solutions and polysorbate 80 to alleviate adherence of the agent to plastic.
Visual demonstration of this method is helpful as the stock and MIC plate solution preparation steps are not typical compared to most antimicrobial agents. These steps are unique to lipoglycopeptide agents and are important to follow in order to achieve reproducible and accurate MIC results. Demonstrating the procedure will be Gina Fisher, a research scientist from my laboratory.
Please note that appropriate safety precautions consistent with Biosafety Level 2 should be utilized when performing the following procedure. Begin by weighing out the appropriate amount of dalbavancin to prepare a stock solution of 800 micrograms per milliliter. Add the appropriate amount of neat DMSO to a sterile glass or plastic tube. Then, transfer the powder to the tube and vortex it. Next, using the 800 microgram per milliliter dalbavancin stock solution, prepare 100x final MIC plate concentrations as shown in columns 1 through 4. These are referred to as the intermediate concentrations. The total volume prepared will depend on the number of MIC panels. Finally, dilute the intermediate concentrations by 1 to 100 in cation-adjusted Mueller-Hinton broth, also known as CAM-HB, supplemented with 0.004% P80. The resulting working concentration of dalbavancin and P80 is twice the final concentration, since the addition of inoculum will result in a 1-to-2 dilution. Using a multi-channel pipette with sterile tips, dispense 50 microliters of each dilution of dalbavancin into the appropriate wells of the 96-well sterile microdilution panel. The MIC plate format allows 8 inocula to be tested per plate. If the panels will not be used immediately, apply plastic film to seal them. Then, place them in plastic bags and store them in a non-defrosting freezer at least -60 degrees Celsius until they are needed. In this demonstration, one freshly prepared plate will be inoculated. To prepare the inoculum, select several well-isolated colonies from an 18 to 24-hour blood agar or other non-selective agar plate. Here, quality control S. aureus and E. faecalis strains are used. Touch the top of each colony with a sterile swab and transfer some of it to a tube containing 1 to 5 milliliters of CAM-HB or saline. Keep transferring until the turbidity matches a 0.5 McFarland standard. Within 15 to 30 minutes of preparation, dilute the inoculum 1 to 100 in CAM-HB to arrive at a final concentration of 5 × 10⁵ CFU per milliliter. The acceptable range is 2 to 8 × 10⁵ CFU per milliliter. Immediately, using a multi-channel pipette with sterile tips, transfer 50 microliters of the final inoculum to each appropriate well of the MIC panel plate. Here, 4 rows are inoculated with each of the 2 isolates, for a total of 4 replicates per isolate. Next, to perform a purity check, use a pipette to transfer 1 to 10 microliters of the solution in the positive growth control to a non-selective agar such as trypticase soy agar with 5% sheep blood. Use a sterile loop to spread the solution over the surface of the plate. Turn the plate 90 degrees and streak again to assure that the inoculum is evenly distributed. Cover the plate and set it aside. In preparation for a colony count, use a single-channel pipette to transfer 10 microliters of the solution in the growth control well to 10 milliliters of saline. Mix and then transfer 100 microliters to a suitable non-selective agar medium such as trypticase soy agar with 5% sheep blood. Using a sterile loop, spread the solution over the entire agar surface. Repeat this process 2 times in different directions to assure even distribution of the inoculum. Next, stack up to 4 MIC panels in a plastic container, ensuring that the top panel is tightly sealed with a lid. Then, place a damp paper towel inside the plastic container and close it securely with the lid. Within 30 minutes of inoculation, incubate the MIC panels, the colony count plate, and the purity check plate in an ambient air incubator at 35 ± 2 degrees Celsius for 16 to 20 hours. The next day, read the minimum inhibitory concentration as the lowest concentration that completely inhibits bacterial growth in the wells as detected by the unaided eye. Determine the number of colonies on the colony count plate. Multiply the number counted by the dilution factor. For example, 50 colonies times a dilution factor of 10,000 equals 5 × 10⁵ CFU per milliliter.
An acceptable range is 20 to 80 colonies, which equates to 2 to 8 × 10⁵ colony-forming units per ml. The concentration of the inoculum is an important variable to control the susceptibility testing in order to obtain accurate results.
Finally, check the purity plate. If all colonies are similar to the colonies used as inoculum, then it can be considered pure. If there are any other colonies present, then there is potential for a contaminant to be present in the MIC panel, and the test should be repeated. Dalbavancin MIC results were compared to those obtained using the agar dilution method. As shown here, agar MIC results for dalbavancin are typically 2 to 8-fold higher than broth microdilution MIC results. This contrasts vancomycin results, which are similar by broth and agar methods. Therefore, agar dilution is not recommended for testing of dalbavancin. Dalbavancin broth microdilution MIC results for quality control should be within expected ranges, as shown here. The S. aureus quality control organism, ATCC 29213, with a very clear modal MIC of 0.06 micrograms per milliliter, has been a good indicator of method variation. If the results obtained are outside of the expected ranges for the quality control organisms, or trending to either the low or high end of the range, further validation of the method is warranted. In addition to validating the method using quality control organisms, dalbavancin MIC data from regional antimicrobial surveillance programs can provide a basis for MIC results to expect in the clinical laboratory setting. As shown here, dalbavancin MIC results for isolates collected in Europe and the USA in 2011 to 2013 were less than 0.25 micrograms per milliliter for 99.9% of S. aureus and 100% of streptococci. Based on these surveillance data, it is evident that dalbavancin MIC results for staphylococci and streptococci greater than 0.12 micrograms per milliliter are rare. If higher numbers are seen, the test should be repeated and/or sent to a reference laboratory for validation.
The preparation of the stock dilutions in DMSO and the addition of P80 to the broth dilutions at a concentration of 0.002% in the final MIC well are the critical steps to obtaining accurate and reproducible dalbavancin MIC results.
As always, but especially in this area of bacterial resistance development, accurate antimicrobial susceptibility results are critical to the clinician's choice of appropriate therapy.